Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth. Hello, welcome to Physics with Beth and Beth. I'm Beth. We are doing our first exam review video. We've had some of you out there request review videos, so we decided we'd post some for the next couple weeks. They are by no means all that you need to use to study for this exam. All right, but they are helpful hints and tips and that I have given to my students over the years and that I continue to give to my students to help them prepare for this exam. Now, I will say that you've worked so hard this year to learn this curriculum, and it's amazing if you just look at where you were in August to where you are now. If it was a whole year curriculum, then you can be really proud of yourself for how much you've learned. But this is not the time to stop. All right, you are on the home stretch. You have worked so hard. Don't throw away all that hard work by just quitting and not studying for this exam. Dig in, find your inner strength, and give it 100% and finish strong, and then you won't have any regrets, all right? But I will be posting in the comments of this video some, in the first comment, some videos of ours that I would go back and review, and maybe not ours, but at least problems that either from a past exam you have or your notes from your teacher, professor, or you can watch our videos as well. But there's some problems that I would definitely what I call classic AP Physics 1 problems that I would review. And we will post those in our comments with this video, okay? Now we're gonna get started on, first of all, the test has changed, so let's get started here. We are now not at 50 multiple choice questions. There are only 40. You get 80 minutes and it's 50% of your test. That means 2 minutes per multiple choice question. Strategy here is keep it at about 2 minutes. Do not sit and stare at a question and try to figure it out for 10 minutes, because it would be tragic to miss getting to the end of the multiple choice section and maybe there were 4 or 5 you did know, but you spent 10 to 12 minutes on one you didn't know. All right, so move. If you get stuck, move. If you are looking at a multiple choice and you can rule out 2 out of, say, 4 of the choices, mark through those, and then you can always come back later and go, okay, you don't have to waste your time. I know it wasn't A or C, but it's got to be B or D. Well, you just increased your chances to 50-50, right? If you were right about A and C not being possible. Okay, so watch that. The other thing that's really important is you are not penalized for wrong answers. So before that 80 minutes is up, you make sure that you have something marked for every single question. Better if you have it blank, 0% chance of getting it right. You actually answer something, even if you don't have a clue, you answer something, you've got a better shot than 0% at getting it right. All right, so that's what I would do. Now the next part is 4 free response questions down from 5. They give you an extra 10 minutes. So you have 100 minutes, which is 25 minutes per multiple choice. In other words, don't spend 45 minutes trying to figure out one of these free response questions. Don't spend 45 minutes trying to figure out all the parts. You need to move if you're stuck. Move on to the next one. Now, if it were me, I tell my students this, I would take 60 seconds to just glance at all 4 free response questions. You'll get them all at once. I would glance at those, and then I would say, oh yes, dynamics I'm more comfortable with. I'm gonna start with that one, even if it's problem number 3. And oh yes, okay, I see a projectile and mixed with a momentum, a conservation of momentum, like a collision of some sort. Okay, comfortable with that. I'm gonna do that one next. Okay, so then there's this rotational one that looks really crazy and I'm not very comfortable with that. I'm gonna wait and do that one last. So do the problems you're more comfortable with, the units, do those first. It doesn't matter if it's 3 and 4, and then come back and do 1 and 2. You get 100 minutes, 25 minutes each is a good estimate of what you should be spending on them. Here's what they're about. They're about mathematical routine. We're actually going to come up with some answers here, not just expressions. Experimental design and analysis, which they've had on the test before. Quantitative and qualitative, which they've also had as free response questions before. And then this translation between representations, it's going to have some graphing and that kind of thing on it, we would assume. So anyway, the other part is you're going to get, the other tip is you're going to get multiple questions, A, B, C, D, E, I, whatever, all of the notations. If you can't get, like you can get A and you can get B, you can't get C, don't give up on D and E or DI and DII. Look at them, and you might be able to do something later on in the problem, later questions in the problem. So check it out before you move on to the next question. Make sure that just because you can't do C doesn't mean you can't do the rest of the questions. So be sure and read through those real quick and then move on to the next problem. Don't sit there and just stare at it if you don't know how to do it. Go to a problem and get some points that you know you can do, okay? Now we're going to talk about equations to memorize. Just really quickly, the good news is they redid the equation sheet and I think it's fabulous. It does a good job of putting some more things on so you don't have to memorize as much. But here's some things, and some of these are just concepts. They're not really memorization, but worth it to look at. Force due to gravity is mg. Newton's second law, F equals ma, absolutely. The sum of the forces equals mass times acceleration is absolutely on the equation sheet. It's just in terms of A. I always like to see it like that. It's just me. Ramp, force due to gravity parallel is mg sine theta. Force due to gravity perpendicular is mg cosine theta. You can absolutely derive that, but it will take a second or two that might be better used on another problem. So I would go ahead and memorize those. Here's what it looks like. Force due to gravity on a ramp is always straight down. It doesn't go along with the ramp. So that means there's a component of it that's perpendicular to the ramp right here, and that's adjacent to that angle, because if that's theta, then this is theta. That's adjacent, meaning cosine. Then here's the part that's parallel to the ramp, and that's opposite that angle, so that's sine. All right, now note that in a exam, they will tell you absolutely do not, on a free body diagram, show your components. So don't show your components. If you needed to draw this out, then do it on the side, not on the actual free body diagram they're going to grade. Also, to note, they might say, make sure that your arrows, do a free body diagram with the arrows representing forces, and make sure they're proportionate to the magnitude of the force. What does that mean? Big, scary terms. It just means if this is a lot bigger force in magnitude than, say, another force, then make the length appropriate to the magnitude. In other words, if you had like a little pulley system, your Atwood, and this was your little mass and this thing is going in this direction, well then you would have tension here and you would have a longer force due to gravity because this thing is moving down. All right, that's what it means, make them proportionate. And then if this pulley had no mass, then you know on this block that the tensions would have to be equal as long as the pulley didn't have mass, and that this little force due to gravity has to be smaller than the tension because it's moving up, right? So unbalanced forces are determining the movement here. And they're saying make the magnitude represent, the length of the arrow represent the magnitude of the forces. That's all it's saying, if you see that. Now, work energy, work is equal to change in kinetic energy. They give you that on your equation sheet, but don't also forget that work equals your change in potential energy due to gravitation and due to a spring. Also apply. In momentum section, I'm kind of doing this by units, but momentum, the change, they give you momentum as mass times velocity, but the change in momentum is, remember this delta always means change in final minus initial. I factored out mass here, but it would be mass times final velocity minus mass times initial velocity. That's what change in momentum means. All right, again, that's more of a concept, but understanding that. For rotational, point mass. Now, for the moment of inertia of a point mass, they may give it to you on the test, they may not, unsure about that, but it's mr squared. Now, what's a point mass? Remember, it's the little object interacting basically with the bigger object with the rigid shape. In other words, you have a kid running on a merry-go-round. The kid is the point mass, the merry-go-round is the rigid object that's rotating on an axis. You have a potter's wheel and you drop a piece of clay on it. The clay is the point mass, and the rigid object that's moving, that's rotating on its axis is the potter's wheel. All right, so for moment of inertia or rotational inertia, those two words mean the same, don't forget. That's mr squared. The same as a hoop is mr squared. All right, now, but remember on a hoop, the radius would be the radius of the hoop. On a point mass, that r is the distance from where it is on your rigid object to the axis of rotation. And what I mean by that, let's say I'm looking down at a merry-go-round and I have a kid that jumps on here. Well, the point mass for the kid would be the mass of the kid and its distance from axis of rotation, which in this case is r. But if the kid had jumped in the middle, then it would have been 1/2 r. All right, so that's what that point mass is. The r is not the radius of the object because the kid's not round, right? So that's what that is. Don't forget that. Then the angular point mass is r, again, that distance from where it interacts with the rigid object, where it lands on the rigid object, I should say, or interacts, times the mass of that point mass times its velocity times sine theta. And in this case, it would be like if the kid was running at the merry-go-round and had a velocity of, let's say, 12 meters per second and had a mass of, let's say, 60 kilograms. Well, if they jump on here, that r is going to be the radius of the merry-go-round. But again, if they jumped on in the middle, it would be that r would be 1/2. Now, sine theta, well, when they're here, it's at 90 degrees, and sine of 90 degrees is 1. Hopefully that makes sense. Now, change in angular momentum is equal to angular impulse. Angular impulse is torque times time, and that's equal to our change in momentum, which is our change in angular momentum, which is your moment of inertia, rotational inertia, times your final angular velocity minus your rotational inertia times your initial angular. Because again, change in means final minus initial, and that I would be distributed. Okay, the sum of the torques is equal to that moment of inertia, rotational inertia, times angular acceleration. That's Newton's second law, but for rotational motion is all that is. Simple harmonic motion, they give you that period is equal to 1 over frequency, but don't forget that frequency is also equal to 1 over period. They're inverse. All right, angular frequency is 2 pi divided by the period, if that comes up. These are really just concepts that period is time over cycles, and frequency is cycles divided by time. And cycles also means oscillations, so time divided by oscillations or oscillations divided by time. These are really just concepts in case they give you time and cycles in a problem. All right, mechanical energy total of a system for simple harmonic, if it's a spring, is 1/2 times that spring constant times that amplitude squared. It's important to know that. And then we go to centripetal. This is Newton's second law, but for centripetal motion is mass times centripetal acceleration. And also on your formula sheet, it says, hey, centripetal acceleration is equal to v squared over r. So I just subbed that in. That's mass times v squared over r. All right, your centripetal force is also the sum of that is equal to mass times r times that angular velocity squared. And then we have centripetal acceleration. This is on your formula sheet. This is not. Centripetal acceleration is also equal to r times angular velocity squared. Now remember, again, what that r means. We've got to think about r. If this isn't a rigid object that's like a sphere, then it's not r about the radius. It is r that's the distance from center of mass to center of mass in centripetal. If you're looking at like the universe and you've got like a planet and a satellite, it's for r is from center of mass to center of mass of the two objects. Okay, then we go into gravitational motion and universe. Now these I would memorize. However, we are going to have a whole review video on these, on how you derive these. For multiple choice questions, it would be great if you could have them memorized, because then that's going to go faster. If it's a free response, they're probably going to ask you to derive them. So you also need to know how to derive them. But little g is equal to big G times the mass of the, if you're talking about the moon, then the moon. If you're looking for little g on the moon, if you're talking about Earth, it'd be the mass of the Earth over r squared. All right, your velocity, escape velocity, is the square root of 2 times g times the big mass. So in other words, if we're talking about a rocket getting off our planet, it would be 2 times big G times the mass of the Earth, not the mass of the rocket, the mass of the Earth, divided by r, and take the square root of all of that. All right, your tangential velocity, let's say we have a satellite, our moon. We could say our moon or satellite. The moon is a satellite. But anyway, what is its tangential velocity as it revolves around Earth? Well, it would be the square root of big G, mass of the Earth, not the satellite or the moon, divided by r. All right, and then our mechanical energy total of a object that is like revolving around the Earth, or an object that is revolving around Saturn, or us revolving around the sun, is -1/2 big G, mass 1 and mass 2, whatever you're talking about, sun and Earth, if you're talking about Earth and moon, divided by r. All right, so that would be the equations. Oh, and then we go to 8. I didn't think about 8. 8 is really more like your kinematics, but it's kinematics in linear and rotational. That's a C, sorry. Don't forget, I mean, really, these are, you can see these in the big 3 equations, but especially like this one right here is really just your first big 3 equation. But don't forget, these are concepts. Velocity is the change in displacement over time. Acceleration is the change in velocity over that time interval. Angular velocity is change in angular displacement, which is delta theta, over that time interval. Angular acceleration is equal to the change in angular velocity over time. It's just to remind yourself of that. Now, really quickly, some places to start. I always get this from students. Oh my lands, these problems, they're scary. I don't know where to start them. Okay, here is my suggestion and my tip that I always tell my students. Let me do this. If it's projectile, if you see projectile motion, you know, the odds are you're starting with the big 3. And what do I mean by the big 3? I mean this V final equals V naught plus AT, and then so on. The first 3 equations on your equation sheet. And so that would be where I would start for that. If it's like a blocks, you see pulleys, you see like boxes stacked, you see a ramp with a box, anything like that, you're probably starting with Newton's second law for linear motion. Okay? Now I'm not saying these work 100% of the time, but I'm saying they're a really good place to start. All right, if you see a change in height, and this can also be a ramp, if you see a change in height, you see a roller coaster, so a roller coaster, you see a ramp as well, you could do a ramp. If you see this change in height, then you're probably going to be looking at conservation of mechanical energy. Okay? Also, if you see a change in height with like a spring, like we've got the roller coaster, you know, we got this roller coaster and it's going like this, but up here is a spring, and then it's going to shoot this box down this kind of roller coaster kind of thing, or hill. Then again, change in height, your mechanical energy before equals your mechanical energy final is a really good place to try to look at that and start. If you see anything moving in a circle, all right, when I say circle, I mean like a satellite going around Earth, a yo-yo that is being spun around, a loop on a roller coaster. So you have a loop on a roller coaster. You have the Earth and you have like the moon here moving in a circle. You have a yo-yo that's being swung around in a circle. If it's moving in a circle, you can kind of, I wouldn't say confidently, but you certainly, this is a good place to start, is your Newton's second law for centripetal acceleration, recognizing that this is v squared over r. Okay, that's a good place to look at to start anyway. All right, so conservation of mechanical energy, Newton's second law for centripetal, Newton's second law for linear, and then if projectile, the big 3. Then if you see any collision, if you see a collision, you're looking at conservation of momentum. So for like a car collision, something like a ballistic pendulum, the car collision, ballistic pendulum, anything like that, then you're looking at that conservation of momentum. So momentum before or initial equals momentum final. Okay. By the way, also if you're moving in a circle with a banked curve, if you have a banked curve, or you have a conical pendulum, you can also start there with that. And I'm not saying it's the only equation you need, but it's a good starting place. And to see, odds are you're probably going to need it. Now, if you have angular collision, what do I mean by that? I mean like the potter's wheel with the clay dropping on it, the merry-go-round with the kid jumping on it. You're going to be starting with that, again, conservation of momentum, but angular momentum this time. Okay? Now, if you have something that is rotating, so you have an object that's rotating, and that object that's rotating, it could be a pulley system again, but pulley with mass. That's very important. These pulleys would be without mass. All right, but with mass, then you're going to Newton's second law for rotation. So Newton's second law for linear, Newton's second law for centripetal motion, moving in a circle, Newton's second law for rotational motion. All right, then again, if you see the spring and you've got these graphs that look like this, you know you're doing simple harmonic motion, right? And you know that you've got period, frequency, you've got the position sine and cosine equations. Okay, so if you see anything like this, you're looking on your equation sheet in that next to last section of equations on the right side, the right column. All right, if you see fluids, you see any fluids going in a pipe. All right, so let me move over here. If you see fluids moving down a pipe, not just fluids, it could be air, right? Because we talk about gas and fluids, gas and liquids being in our fluids. But if you see any pipes with fluid, or anything like dealing with pressure, with dealing with buoyancy with fluids, dealing with density with fluids, all of that, you're going to be in that last section on your equation sheet, where you're going to see the formula for buoyancy, for pressure, for density, and then also Bernoulli's and the continuity equation are all going to be there. So that's going to be the last section of your equation sheet. And let's see, blocks, pulleys, I think we've got that with forces, and I think that's probably the big places to start. And just as an overall, I don't even know where to start this problem. I'm not saying these work 100% of the time, but I'm saying that they're a good starting point to look at if you don't know where to start on your problem. And you might be using them, and we might be using a F equals ma with a big 3. Or you might be using, if it's the ballistic pendulum, you're using conservation of mechanical energy with the conservation of momentum. All right, so you might use a couple of these together, but they're good starting places on linear movement, rotational movement, and then centripetal movement, and this change in conservation of mechanical energy, conservations of momentum, both linear and angular, simple harmonic, and fluids. So anyway, there you go. This was a long video. I'm sorry, these review videos are probably going to be kind of long. It's hard to shorten them with these big long problems and lots to cover. But anyway, thank you for sticking with me. If you like this video, give it a thumbs up. If you haven't subscribed yet, please do. We would love that. Or pass it on to a friend who's also studying for the AP exam if you find these helpful. And thank you for watching, and happy physicsing.